Hello, everybody. My name is Erfan Asi, and in this session, I want to present our new work about a control architecture for probably correct autonomous driving. So recent advances in computational software and electronic devices have led to development of several automated safety features for modern vehicles like adaptive cruise control and lane keeping systems. However, the dynamically changing nature of urban driving environments, together with the necessity of obeying a diverse set of traffic rules, limit the performance of these safety systems to relatively low complexity driving scenarios. And to overcome this problem, a variety of control and planning algorithms have been proposed, which are mostly based on model predictive control algorithm. But one of the biggest challenges of these methods is their computational cost, where any increase in the complexity of the models they use, like the dynamic model of the vehicle or the model of the environment, can lead to an explosion in the runtime. And as a result, these approaches cannot handle real traffic scenarios. Now, to address that concern, here we propose a two-level control algorithm to follow a given reference path as close as possible and satisfy a set of traffic rules with the focus on meeting the runtime performance criteria, so to have an useful algorithm for real-world applications. To formulate the problem mathematically, we need to define some of the elements. So first of all, we refer to the autonomous vehicle as ego, and we consider discrete time continuous space models for dynamics of ego and other vehicles in the environment. And we assume the dynamic model of ego is given by such an equation here, where zeta is the state vector of ego, u is the control input, and f is a general function. And the state vector consists of the position of ego, its heading, and its velocity component. And the input vector consists of the steering delta and the throttle or braking gamma. The model of environment consists of lanes, traffic signs, and traffic participants like vehicles, bicycles, and pedestrians. And here, for the simplicity of notation, we have assumed that all of the traffic participants are vehicles, but our method is generally applicable to any problem. Also, we assume that sensors and cameras of ego are able to provide the necessary information about nearby objects in the environment. The given reference path is an untimed finite sequence of waypoints represented by P, and each waypoint P consists of the position of the waypoint and its heading. And we assume they are in the middle of the lanes, as you can see in this figure, and they are equally spaced from each other. We also consider an objective function for ego, which aims to minimize the energy of the vehicle, provide comfort for driver by minimizing the changes in the inputs, and minimize the error with respect to the reference path. To formulate the traffic rules mathematically, we use signal temporal logic specifications, where you can see the syntax here. And we consider the STL specifications in the state space of the vehicle. So to verify the satisfaction of each traffic rule, we need to check the state vector of the vehicle. And we consider the set of active rules at each time step by phi active, which is a subset of the set of whole traffic rules. Here as an example, we have provided the collision avoidance constraint formulated by this STL specification, where the collision avoidance term inside the parentheses is the predicate that checks the minimum distance of ego with respect to other objects in the environment. And the formula requires that predicate to be true over the MPC's horizon, which is denoted by big H. Now, if we denote the total finite time steps of ego's operation by big T, which is unknown, we can formulate the problem as below. Given the environment of ego, its dynamic model, the given reference path, and the set of traffic rules, we desire to find the control sequence that obtains the minimum value of the objective function all over the time steps of the ego's operation and satisfies the dynamical and traffic rules constraints. Now here we have a general overview of our approach. We propose a two-level controller for driving the autonomous vehicle from its initial state to the goal point and satisfy the runtime performance requirement. At the high level, we formulate an MPC problem, which uses a simple representation of ego's dynamic model and its environment to compute the optimal control input at each time step. At this level, the set of traffic rules that ego must satisfy are imposed as mixed integer linear constraints to the MPC. Then the optimal control from this high-level controller is used in the low-level controller to forward simulate the trajectory of ego in a complex model of ego and the environment. STL-based runtime monitoring techniques are used here in this level to verify the correctness of ego's behavior. In other words, the high-level controller plans with simplified models and does the most of the work by finding the optimal control inputs that minimizes the objective function, while the low-level controller tries to verify the behavior of ego under the optimal control input with respect to detailed models and makes necessary adjustments to that optimal control input to find the best control input that is safe and satisfies the traffic constraints. Now, in the following, we detail each level of the algorithm. In the high-level controller, as a simplified vehicle model, we use simple bicycle model for the dynamic model of ego, and we also use the same model for predicting the trajectories of other vehicles. Moreover, as a simplified environment model, we consider all vehicles in the environment as point masses, and to impose the safety constraint as a linear constraint to the optimization problem, we check the first norm of the distance between ego and other nearby vehicles in the environment to be bigger than a known safety distance. Now, to formulate the MPC problem, we compute a desired trajectory over the MPC horizon based on the reference path, which is a sequence of h waypoints, and each waypoint consists of a desired x and y position, desired heading, and desired velocity, where the position and heading, they match one of the waypoints in the reference path, and the desired velocity is adjusted with respect to the position of ego in the traffic. So eventually we can formulate the optimization problem as here, where the optimal control input is denoted by U star, and this will be used in the next level of our algorithm. In the low-level controller, as a detailed vehicle model, we use four-wheel vehicle model, which has the same inputs as the simplified vehicle model. And in the detailed environment model, to verify the safety constraint, instead of point masses, we consider the bounding box of all vehicles. In the last step of this level, we first forward simulate the trajectory of ego using the detailed models and the optimal control from the high-level controller, and we construct runtime monitors to verify the satisfaction of traffic rules. In the case the optimal control does not satisfy all constraints, in the control space, we random sample around the optimal control to find a near optimal control input that satisfies all traffic constraints. Now, as a summary of our approach, in the high-level controller, we use simple bicycle model for the dynamic model of ego, and we consider vehicles as point masses to verify the satisfaction of collision avoidance constraint. Then we formulate an MPC problem to find the optimal control input, and this control is used in the next level controller. The low-level controller uses that optimal control to forward simulate the trajectory of ego with respect to detailed models, and it constructs runtime monitors to verify the satisfaction of rules with respect to the trajectory of ego. In the case the optimal control does not satisfy all constraints, the low-level controller perturbs that optimal control slightly to find the best control that satisfies all constraints. Now, to validate the effectiveness of our algorithm, we have designed 4 urban driving case studies in a simulator named Carla, where each scenario mostly focuses on a specific feature of our algorithm. In all the scenarios, their reference path is given by the red solid line. In the first case study, named as comparison, we desire to compare the performance of our algorithm with some existing works based on nonlinear MPC. The second scenario, named as traffic rules scenario, shows the performance of our algorithm with respect to a variety of traffic rules. The third scenario, named as safety scenario, shows the importance of low-level controller to provide safety with respect to other vehicles in the environment. And the last case study shows the scalability of our algorithm with the number of other nearby vehicles in the environment. In the comparison scenario, as you can see, our method achieves better runtime performance with respect to the nonlinear MPC, in addition to the fact that the speed profile of our algorithm is better and is able to achieve higher speeds compared to nonlinear MPC implementation. In the traffic rule scenario, again, we have promising runtime performance. And also from the speed profile of Ego, we can see how it satisfies all of the traffic rules. In the safety scenario, we have implemented our algorithm once without monitors and once with the monitors. And as you can see, although the without monitor implementation achieves better runtime performance, but the with monitor implementation is able to always keep a minimum safe distance from all other vehicles in the environment and always satisfy the collision avoidance constraint. In the last scenario, where we have 121 other vehicles in the environment, we desire to show the scalability of our scenario. And as you can see, our algorithm is still able to have a good runtime performance and always keep a minimum safe distance from all other vehicles in the environment. So as a conclusion, we have proposed a two-level control approach for fully autonomous vehicles, where in the high-level controller, we formulate an MPC problem based on simplified models. And in the low-level controller, we construct runtime monitors based on detailed models to impose safety and correctness. And we obtain substantial performance improvements in terms of quality and runtime. Thanks for your attention, and I would be happy to hear your comments and questions.